All right, this is a post-mortem, a real horror story for any engineer, actually. It's about how one single button click, something so simple, triggered a catastrophic failure that almost took down an entire service. Let's dive right in. So, picture the scene. It's one we've all coded 1,000 times, right? You've got a user, a payment screen, and that one big, shiny button, Pay Now. But here's the catch. They're on a spotty public Wi-Fi connection. They click, a spinner pops up, and it just keeps spinning. So what do? Exactly what you or I would do. They click it again, just in case. And that first click, it was perfect. It sent a beautifully formed request on its way to our servers, ready to be processed, exactly like we designed it to. In a perfect world, that's where the story would end. But that second click, born from totally normal user impatience and a flaky network, it launched a duplicate request. And in that one moment, our system, which we thought was rock solid, began to quietly tear itself apart from the inside. Now, to the user, everything looked fine. Their screen eventually showed a thank you page. But behind the scenes, our backend was in a full-blown panic. Two identical requests had arrived, and the system, in its innocence, was about to process both of them. And the fallout was just a cascade of failures. The payment gateway hit twice. The customer double charged. Our database, it committed two identical order rows. This, of course, triggered an automated refund workflow, which created the storm of confusing emails. And naturally, our support team was completely flooded with tickets from a very, very angry user. But the absolute scariest part? Look at that last bullet point. No errors were logged. As far as the system was concerned, it had just successfully processed two completely separate orders. Everything worked perfectly. So in this explainer, we're going to dissect this failure completely. We'll look at the initial damage, we'll figure out why all the common fixes are basically useless, and then we'll uncover the only real architectural solution. And finally, we'll redefine the roles of our front end and back end to build a system that's truly resilient to the absolute chaos of the real world. So the first question any developer asks is, wait, why didn't the front end protection work? This is the most common and honestly, the most dangerous assumption we all make, right? I mean, we all write this code. On click, disable the button. It's like the first thing you learn in Frontend 101. It feels like this solid defense, but it's not. It's not a defense at all. It's really just a polite suggestion. It's a UX enhancement that provides zero, and I mean zero, actual protection. And this right here, this is the latency trap. It's so insidious. The user clicks, and that first network request is fired off instantly. But because the network is slow, the JavaScript that's supposed to disable the button gets delayed. And in that tiny window, it only takes a few hundred milliseconds. The user clicks again, and bam! A second identical request is now flying through the network. By the time the UI finally catches up and the button grays out, the damage is already done. It's too late. What we're looking at is a classic race condition. This is the phantom menace in our story. It's not just about things happening fast. It's about them happening in an unpredictable order. We had two operations that were racing each other, and we had no idea who would win. We built our entire system on the assumption that one click equals one payment, but the unpredictable nature of the internet proved that assumption was fatally wrong. So if the client is fundamentally unreliable, where do we build our fortress? The answer has to be on the server. The only real fix is an architectural principle called idempotency. The core concept here is so simple, but it is incredibly powerful. For any operation that changes something, like making a payment, the client has to generate a unique ID. This is usually a UUID, and you send it along in a header. Think of it like a unique fingerprint for that specific transaction, created before the request is even sent. Okay, let's just walk through this, because this is where the magic happens. When request number 1 arrives with its unique ID, the backend's never seen it. So it processes the payment, creates the order, and this is the critical part, it stores the successful result and keys it by that ID. Now, when the duplicate request shows up with the exact same ID, the backend does a quick lookup. It sees the ID, it recognizes it, and it immediately stops. It does not reprocess the payment. Instead, it just pulls up the saved response from the first successful request and sends that back. The client gets a success message, and our data stays perfectly clean. And what this means is that the backend becomes the undisputed source of truth. It just doesn't matter if the client sends one request or 100. For this specific user action, 1 + 1 will always mathematically equal 1. This, by the way, is the exact strategy used by companies like Stripe to process billions of dollars safely.
So this completely changes the job of the front end. It's no longer the system's bodyguard. It's more like a helpful concierge. Its job is just to give the user clear and timely feedback.
This comparison makes that division of labor crystal clear. On one side, you have backend Idempotency. Its role is to be the source of truth. Its function is to prevent data corruption, period. On the other side, you have front-end debouncing, disabling that button. Its role is purely user experience. Its function is just to visually communicate, hey, we heard you, we're working on it. One provides absolute protection, the other provides necessary clarity. And you really do need both.
So what does our system actually look like after we've installed this architectural armor? How does it behave under fire out in the wild?
Well, the results really speak for themselves. A single, normal click works perfectly, of course. A frantic double click from an impatient user, totally harmless now. A slow, unreliable network connection, it no longer introduces the risk of duplicate charges. And even these automated retry storms you get from other services hammering your API, they won't cause data corruption anymore. The system is now resilient by design, not by chance.
This entire incident, this whole fix, it all boils down to one fundamental shift in mindset. It's a core engineering principle about where we can, and more importantly, where we cannot place our trust.
And this is the key takeaway for all of us. Users will always double-click. Networks will always be flaky. Your system doesn't break because users misbehave. It breaks because you trusted them. You trusted the network. You trusted the client. You trusted that events would happen in a nice, orderly sequence. And in the chaotic world of distributed systems, robust architecture is the only thing that can protect you.
Look, if you have ever spent hours or days or maybe even a week chasing some phantom bug that just disappears the moment you try to reproduce it locally, you know exactly how painful these race conditions are. If this resonates with you, like this explainer and subscribe for more deep dives like this one.
सब्सक्राइब करो अगर आप सिर्फ कोड नहीं इंजीनियरिंग सीखना चाहते हो। थैंक्स फॉर वॉचिंग।